Daniel then. So without further ado, very pleased to introduce uh, his talk on Instantons on Joyce-Karigiannis Manifolds.
Okay, yeah, thank you very much for the nice introduction. Also, thank you very much to the organizers for organizing this very nice event. I already learned a lot during this week, and of course, I'm also very happy that you allowed me to speak here. Great honor. So this talk is about Instantons on Joyce-Karigiannis Manifolds. The plan is that I will spend maybe the first 15-20 minutes to talk about Joyce-Karigiannis Manifolds. I will explain a small variation of the original paper, which is a bit shorter and will have two mildly interesting consequences. And the second half of the talk will be on instantons on these manifolds. So let's see how far.
Daniel, if you could just speak a little closer to the mic, we're not getting a lot of return from you just now.
Okay. Like this? Is it better?
That's excellent. Thank you.
Okay, very good. And so I have planned things to say for around 45 minutes. So please, if you have questions, fire ahead. Very good if you ask questions. All right, so let's get started. First slide, I will basically skip. That's a review of what's G2, but we already had 2 G2 talks, so I can keep that short. The important part is a G2 structure is torsion-free if and only if it's closed and co-closed. That's the blue box here. What we will need more though, so I will spend a minute to talk about that, is product G2 structures. So if our G2 form is this phi thing on the top, there's a 3 form on R7 with stabilizer G2, then we can do the following. If we write R7 as R3 plus H, and we put coordinates x1, 2, 3 on R3 and y1, 2, 3, 4 on H, then we can write our phi as follows. We have phi equals dx1, 2, 3 minus sum over dxi, which omega I, where the omega I is this hyperkähler triple on H that you see here, and where dx1, 2, 3, the coordinates on R3. And likewise, we also have this very nice formula for star phi, which I will always denote as psi here. So you can also write this star phi using the omega I in this way. And this linear algebra extends to product manifolds. So if you have a Calabi-Yau fourfold, complex dimension 2, and you times it with a 3 torus, then you get a torsion-free G2 structure on T3 times X. And this will not have holonomy equal to G2, but strictly contained in G2. Okay, that was the pre-waffle, and now we come to the manifold construction. So the ingredients we need is a G2 manifold M with a G2 structure phi, and a G2 involution iota, so that's a map that squares to the identity and full spec phi to phi. And now you may ask, what's the point? I want to construct a G2 manifold, I need a G2 manifold. Well, the point is, maybe you have something with holonomy strictly contained in G2, and then you can use this construction to bump it up to something with holonomy equal to G2. So that's the idea. So take a look at the bottom left. There I drew for you M mod iota. That's an orbifold, which is smooth in most points and has orbifold points wherever iota had a fixed point. Now let's write L for the fixed point set of iota, and it follows from the fact that iota preserved the G2 structure that L is an associative submanifold. So it's 3-dimensional and associative. And in the following, we will also assume that there is some lambda, a closed and co-closed one form on L, which is nowhere vanishing. Oh, and also I never said this, but we also assume that M be compact. Okay, so once we have this L, let's take, on the bottom left in this picture, let's take a neighborhood U of L. That's this orange-pink shaded region there. And when we have such a neighborhood, one thing we can do is we can take the pre-image of under the exponential map in the normal bundle. And now, if on the left-hand side we mod out by iota, then on the normal bundle we want to mod out by plus minus 1. And so we have the exponential map being a map between this orange thing on the bottom right and the orange thing on the bottom left. And I can also, if I want, I can also throw in a scaling. So for some number t, I have the map times t. That's the map on the normal bundle, which just scales in the fiber direction. And that then gives me the map xt. Now on this normal bundle, I can do, for example, the following thing. I can use my lambda to define a complex structure. And a complex structure is defined as follows. It's just by taking the cross product with lambda divided by norm lambda. And then you can use the properties of the cross product to check that this actually squares to minus the identity, so that this actually defines a complex structure on mu. And using this complex structure, we can, if we want, write our new mod plus minus 1 in the following form. We can write this as an associated bundle as the frame bundle of new times C2 mod plus minus 1, where U2 acts through the standard action on C2 and acts on the frame bundle of new using this complex structure we just defined. Now, yeah, so we have this, and similar to this new mod plus minus 1, we can write out another associated bundle. We can define P to be the frame bundle times X Iguchi-Hansen space, where X Iguchi-Hansen space, that's the blow up of C2 mod plus minus 1 in the origin. That's it's a 4-manifold, a hyperkähler 4-manifold. And this bundle P now comes with map rho, which is given as follows. In the Iguchi-Hansen component, it's just the blow-up map. So the blow-up map from X EH to C2 mod plus minus 1. And in the frame component, it just does nothing. So that's our map rho. Now that we've defined these players in the game, then we are ready to write down the resolution of our G2 orbifold. And that's the following. We say that NT is the union of the regular part of the orbifold plus this pink region in P on the top right, modulo the equivalence relation, which is given by xt composed with rho identifying points. So xt composed with rho identifies points in the pink region. And then this thing will be a smooth manifold, and yeah, we write it down for t between 0 and 1. T is called the gluing parameter, and then later on we want to take t very small. So far that was only about the smooth manifold, and I didn't say anything about G2 structures, but now we come to how you get a G2 structure and eventually a torsion-free G2 structure on this guy. So here are again our players in the game, and how it will work is I will write down G2 structure on the orbifold, G2 structure on P, and then we glue these guys together. So here's how to do this. On the orbifold, we automatically have a G2 structure because, well, remember, iota preserved phi, so phi descends to something on the orbifold. Then the next thing we do is take some orthonormal frame on L, and as the first frame vector, we take lambda divided by norm of lambda. That's our E1. And as E2, E3, you choose anything. Just somehow extend it to an orthonormal frame. Now, you can't do that globally. In general, you can't do that globally. But it will turn out it's enough if you can do that locally, because these G2 structures, by P we define, don't actually depend on the choice of E2 and E3. So you may as well think of this being globally possible if you want. So once you have chosen your E1, E2, E3, you can do the following. If you're in some point in L, say X in L, you can write your phi X as E1 to 3 minus sum over EI wedge omega I, or some two forms omega I hat. So this is because L is associative, and this resembles this product structure from the first slide. Now, what you can also do, so right now these omega I hat are only defined in X, but what you can do is you can parallel transport them along the fibers of mu mod plus minus 1, and then you get omega I hat, some two forms on the total space of this vector bundle. So two forms on omega mod plus minus 1, which are parallel on the fibers. Once you have these omega I hats, now we are pretty much ready to write down the phi p. That goes as following. You can see this formula for phi p in the top right, and that uses some two forms omega I. And I want the omega I to be characterized as follows. First, they should point in the fiber direction, and that part is a bit vague. That would need some effort to make that precise, but they should point in the fiber direction as indicated by the little arrow, and they should have the following property you see on the top left. When you have some point x in L, then we want that omega I restricted to a fiber px is exactly the blow-up of these omega I hat from the fiber of mu mod plus minus 1. And so once I got hold of these omega I, then I can write down the phi pt as it's written there, again resembling this product structure from the beginning. So I can write down phi pt equals E123 minus t squared and sum over EI wedge omega I. Now in general, this thing need not be closed. It's going to be pretty close to being closed though, because you can see these EI are closed, and the omega I, well, they're the hyperkähler triple from the Gucci-Hansen space, so they're at least closed in the fiber direction. But it could happen that the omega I has some component in the L direction. So what one can do, and what Joyce-Karigiannis did for us, was write down a correction xi, such that phi pt plus xi is a closed treeform, a closed G2 structure. And they give this xi very explicitly, and so that it has a small norm. So it's not just any xi, but just a small correction of the phi pt. So once we have this, then we have, remember, we have our original G2 form phi, we have the phi pt tilde, then we can write down the G2 guy on the whole manifold. Take R to be the function which measures the distance to the associative L, and measure the distance in the original G2 structure of phi. Then we define phi nt, as it's written here, is phi tilde pt close to the associative. So remember, t is the gluing parameter, it's very small, so r less than or equal to t to the 7 over 8 means r is very small. And we define it to be phi away from the associative. And it turns out that there is a way to interpolate between these two guys so that phi and t still is a closed form. So you can't do anything you want. If you just literally cut off the phi to the phi p tilde, then it won't be closed. But if you do it cleverly, you can interpolate between the two guys, and then you get a closed G2 form phi and t. Find everywhere on the manifold. Now, we can do the similar thing for psi pt tilde, and psi nt. So here's what I mean by that. You see, this phi pt was defined to look like the product G2 structure from R3 times H. And we can write down a similar looking thing, which looks like the 4 form on R3 times H. That gives me the psi p. Then again, I must prove that such a correction exists, and that I can do this cutting off cleverly, and that gives me the psi nt. Now the thing is that when phi is closed, psi is closed, but in general you will not have that star phi equals psi. Because if you had this, then you would have gotten yourself a torsion-free G2 structure, because phi is closed and co-closed. But the problem is exactly that you're not done yet. The G2 structure is not quite torsion-free yet. So here's how to go from here. Here's how to get a torsion-free G2 structure. One existence theorem that we have for the existence of literally on-the-nose torsion-free G2 structure is Joyce's theorem. And that says on a 7-manifold with G2 structure phi, which is closed, and the 7-manifold should satisfy, or the G2 structure should satisfy injectivity radius bigger than C times T, Riemann curvature tensor less than or equal to C times T to the minus 2. If you have a psi such that star phi minus psi, this difference measured in the L2 norm less than or equal to T to the 7 over 2 plus epsilon, then for small t there exists a torsion-free G2 structure phi tilde on our manifold. Now the actual statement of the theorem also involves a C0 and an L14-1 estimate, but these are quite mild estimates. This L2 guy, that's the tough estimate to satisfy. Now the annoying thing that you will find is, if you look at the G2 structure that I wrote down for you, the phi nt, it will not satisfy this estimate. We only have that star phi nt minus psi nt is less than or equal to C times T to the 18 over 8, which is not good enough. So if for some reason you really, really want a torsion-free G2 structure, there are at least two things you can do. The first thing was done by Joyce-Karigiannis in the original paper. What they did is they found certain corrections for phi nt and psi nt, so that when you add these correction terms, then this difference between the corrected phi and the corrected psi will actually be smaller than T to the 7 over 2. There is one other thing that one can do, and that's what I call the simplification, but I guess if you really find it simpler, depends on your point of view. And here's what you can do. You could use, instead of just using this general purpose theorem with the L2 norm, you could use norms which are particularly adapted to the manifold. So,
Daniel?
yes.
Can I believe when you hold the mic with your right hand, it's much better than with the left hand, so maybe you're squeezing the actual tensor.
Okay, so is it okay like this?
This is excellent.
Okay,
but when you change hands, it's not. So.
Okay, I will just stop moving. But yeah, thank you for pointing that out for me.
Cheers. Yeah.
Right. So what do I mean by norms adapted to the manifold? Well, if you take, so remember we took R to be the distance from L, from the associative, and then we use weighted Hölder norms, which are denoted like this: C, K, alpha, beta, T. K, as usual, is the number of derivatives, A, the Hölder exponent, and beta T tell you that you are using the weight function T plus R to the minus beta. So you can see this is very much adapted to the manifold, because this function R doesn't really make sense on a general G2 manifold. That's a special thing for this Joyce-Karigiannis situation. And now if you want, you can check what estimates do you get in this new norm, and there you get d of star phi minus psi measured in this funny norm less than or equal to T to the 25 over 8. And the existence theorem for this norm, so if you reprove the original existence theorem of Joyce in these new norms, looks like this. If we have this G2 structure phi and T, and the four-form psi, such that d of star phi minus psi measured in this norm is less than or equal to T to the 1 minus beta plus alpha plus epsilon, then for small t there exists a torsion-free G2 structure phi tilde on M. And here, as before, epsilon is something bigger than 0, alpha is the Hölder exponent, And now beta is the weight parameter, which must be between -4 and -2. So one fun arithmetic exercise that you can do is check that this estimate from before the theorem is actually good enough to apply the theorem. So take alpha roughly 0, beta roughly -2. Then we, according to the theorem, we need the estimate t to the 3 plus epsilon. And that's exactly what we have. We have t to the 25/8, which is 3 plus epsilon. Okay, so that's one way to get torsion-free G2 structures on the Joyce-Karigiannis manifold.
Can I just?
Yep.
Can you just say something about these walls, about -4, -2? So what's the intuition? What's happening when you cross one of these two walls?
Yes, that's an important question. So for enthusiasts, I added this slide, which explains how it's being.
Thanks.
And also where the walls come from. But just so to get this on the record, the -2 comes from the decay of harmonic forms on Iguchi-Hansen space. And the -4 comes from the fact that if in our blow-up analysis we extract a limit on the regular part of the orbifold, this will extend to, or this will define a distribution on the whole manifold if it doesn't blow up too fast near the singular set. And that's where the -4 comes from. Yeah, but I didn't want to discuss this, so this is something to look at later. Maybe if there's time at the end, we can talk about that more.
Can I ask you a question also, or
Yep.
Sorry? Can I?
Yeah, please.
So in the previous slide, so I understand these weighted spaces are very adapted to your specific situation, so that you can get around and solve it. And maybe if you have a different construction of G2 manifolds and you would like to apply to a theorem like this, you want, maybe these function spaces are not the most natural. But my point is, you stopped asking that star phi and psi being closed for their exterior derivatives to be enclosed. So is there an analog of Joyce's theorem just with usual spaces that you just require that the exterior derivative of star phi and psi be close to each other? So the same hypothesis, say, as in Joyce's theorem,
yep.
But instead of having this estimate in red, you have an analog of this, but with an exterior derivative instead?
Maybe when he says C0 alpha estimate, does that mean on the D of star phi minus psi or on star phi minus psi?
That means on star phi minus psi.
Oh, okay, I see.
So you don't really get around this estimate.
But you do exchange the L2 and the L14-1 for a single holder estimate.
Well, I mean, the L14-1 is maybe kind of contained in this D of star phi minus psi estimate.
Uh-huh.
Okay.
I see. Okay, thank you.
Yep. Yep. Okay. Right. Yeah, any more questions about this this existence business here? Okay, then let me inform you about the two mildly interesting consequences that I promise. First is, remember in Joyce's theorem we had this requirement, or we needed these estimates for the injectivity radius and the Riemann curvature tensor. And in this new theorem we don't have these requirements. So that in particular implies that you can now resolve the connected components of L at different length scales. These two requirements, injectivity radius and Riemann curvature tensor, ruined that before, because the injectivity radius was basically given by the bold size of Iguchi-Hansen space, and you need one estimate for the injectivity radius on the whole manifold. So if you have different components, with different injectivity radii, you must have that the worst injectivity radius satisfies some estimate. Well, previously you needed this, now you don't. So this gives you a B0 of L-dimensional family of torsion-free G2 structures. So before you had this one gluing parameter T, and now if you like, you can have different gluing parameters for the different connected components of L. And another mildly pleasant consequence is that, so if Joyce-Karigiannis wrote down these corrected forms for us, if you throw these corrected forms into the new theorem, then you get a bit nicer estimate. You get the measured in the C0 norm difference between phi tilde and phi, so torsion-free guy and the approximately torsion-free guy, is of order t to the 1 minus epsilon. Before it was of order t to the 1 over 8. And if you want, on T7, you can even make one extra correction, and then you get order t to the 4 over 3, where before we had t to the 1 over 2. And now, if you don't care about estimates, I will come back to this at the very end of the talk, when I tell you why I'm so obsessed with these estimates, why I really want to have them. One example of the construction, which is straight taken from their paper, is the following. Take a sextic in CP2 called C, and take X to be the double cover branched over C. Then we know that X is a K3 surface, and as we've seen before, T3 times X has a torsion-free G2 structure. So let's denote this by phi. Then on X, we can define two maps. First, we have the map alpha, which swaps the sheets. And then we have beta, which is a lift of the complex conjugation map from CP2. Then you can extend alpha and beta to maps on T3 times X. And there are many ways to extend them, but in particular, there is one way to extend them so that alpha and beta preserve phi, and the fixed point sets of alpha and beta are disjoint. And in particular, you find that the fixed point set of alpha is two disjoint copies of S1 times C, and the fixed point set of beta is two disjoint copies of S1 times S2. And remember, we needed a closed and co-closed one form on L. And in this case, you see the fixed point set of alpha and of beta both contain an S1 factor. So we can just take the coordinate one form in this S1 direction. This is then a parallel one form. So in particular, it's closed and co-closed. And also it's nowhere vanishing. And then this existence theorem tells us that the resolution n of T3 times X mod alpha beta carries a torsion-free G2 structure. And furthermore, you can check that pi 1 of n equals 0. So in fact, this G2 structure has holonomy equal to G2. Okay, and we will come back to this example. I will write down one G2 instanton on this manifold. But first, are there any questions about the manifold construction before I move on? Okay, that's good. Then let me tell you about instantons. The definition: a connection A is called instanton if Fa wedge psi equals 0. So, for example, if you have an anti-self-dual instanton, then it's called A, the anti-self-dual instanton, then you can check that F pi star A wedge psi equals 0. So you get a bunch of G2 instantons by pulling back ASD instantons. Similar with Hermitian-Yang-Mills connection. If you pull back Hermitian-Yang-Mills connections, you also get G2 instantons. And as before, this linear algebra carries over to the product manifold case. So if we have an ASD instanton on a K3 surface, and we pull it back to T3 times K3, then we have a G2 instanton on T3 times K3. So let me tell you how to glue instantons. So here we see again the same picture from the manifold construction, orbifold on the bottom left and the bundle P on the top right. And just as we glued the G2 structures, I will now explain G2, some connection on the bottom left, some connection on the top right, and then we will glue these guys together as well. So here's how that goes. First, take some bundle E0, theta, so bundle E0 with connection theta on the regular part of the orbifold. And to make notation easier, let's assume that the normal bundle mu is trivial. It doesn't really matter for the connection, but for the construction, but it makes things easier to write. The other notation we need is MASD for the moduli space of ASD instantons on Iguchi-Hansen space. And so if we have this, then consider a map S from L into MASD. This then gives rise to a tautological connection S of A on the bundle S of E over P, which is characterized by the following property, the property that if you restrict S of A to some fiber Px, little typo there, so the fiber Px, then it's the same as the connection given by the map S, so that should be equal to S of X. And now you have this theta, you have this S of A. You cannot always glue them together. There's some topological compatibility condition that they must satisfy. And here's the compatibility condition. You want that the holonomy of theta around L and the holonomy of S of A around infinity agree. So here I mean that, the following. If you look at L, there's a non-contractible path around L. And if you shrink and shrink and shrink and shrink this path, and you look at the parallel transport along this path, then, well, this may have a limit in your gauge group, or it may not. And I exactly require that the limit exists and be equal to the limit of S of A at infinity. This is only well defined up to conjugation. So you have, if these two holonomies agree, then you can glue them and get some bundle ET with some connection AT over the manifold. And so far, there was no mention about G2 instanton. And if you just take any random theta, you will be very far away from a G2 instanton. So let me tell you how you get a connection that's close to a G2 instanton, and then how you can perturb it to a literal G2 instanton. So the first ingredient we need is a Fueta section. And to this end, well, I said that Iguchi-Hansen space is a hyperkähler manifold, and it's a theorem by Nakajima, which says that the moduli space of ASD instantons over Iguchi-Hansen space has itself a hyperkähler structure. This hyperkähler structure is induced by the hyperkähler structure on Iguchi-Hansen space. And then when we have this hyperkähler structure, we can write down the Fueta equation for some map S from L to MASD. And you see the equation here. I1, I2, I3 is a hyperkähler triple on MASD. And E1, 2, 3 is an orthonormal frame on L. And how exactly you pair E1, or E1, 2, 3 with I1, 2, 3, how you pair these things up, that's being told to you by the G2 structure. If you remember, for point X in L, the G2 structure phi contains these terms, well, EI wedge omega I, and this exactly tells you how you match up the orthonormal frame with the hyperkähler triple on MASD. And now comes the theorem. Why do we care about Fueta sections? Well, if you have that theta is a G2 instanton, and S satisfies the Fueta equation, then we have the following theorem. If theta is infinitesimally rigid and S is a constant section, taking a rigid ASD instanton as its value, then there exists a little correction, little at, such that at plus little at is a G2 instanton with respect to psi tilde nt. Now, it's of course extremely unsatisfactory that we ask the Fueta section to be the constant section. So there's one more thing that I can say, which is not much, but a little bit more. That is, if theta and S, now S viewed as a Fueta section, are infinitesimally rigid, and we have this pre-gluing estimate, f at wedge psi tilde nt less than or equal to t squared, then again we can perturb at to be a G2 instanton. And now a remark: if theta is a flat connection, M is a flat manifold, if M is the 7 torus, then it's not so hard to show that we have this pre-gluing estimate. We have fa wedge psi n less than or equal to t squared. Now the annoying thing that you see is this is a psi and not a psi tilde, and so you really want a good estimate for the difference between psi tilde and psi to satisfy this pre-gluing estimate. So that's why I was so obsessed with these powers in the beginning. Okay, so much about the general gluing picture for instantons. Questions about this?
Can I? Yeah.
Yep, please.
Can you at least conceptually think of weakening the rigidity assumption in favor of some actual transversality? I understand this would make everything much harder because by being rigid, you are more comfortable than to perturb. Mm-hmm. But is this the kind of situation in which rigidity is just a simplifying assumption, and the actual condition you're trying to imply is some transversality in the deformation theory of the instanton?
Yes, that's probably the picture. So the model case is the gluing of non-rigid ASD instantons, and there you have this Kuranishi map, which tells you, well, sometimes you can glue them and sometimes not. You have this map into the obstruction space. And there is probably a Kuranishi model in this situation, which tells you, well, if you have a non-rigid theta, a non-rigid Fueta section, then there is some map into some obstruction space. I'm not sure what this obstruction space would be, but the zeros of this map then tell you which ingredients can you glue together. Does that answer the question, or not really?
Well, if you haven't thought about it, sort of, then the question is probably just absurdly hard. So I'm saying is, it looks like the kind of hypotheses that one could try and weaken in the search for a broader array of examples, just in which rigidity can be replaced with some transversality assumption. Instead of assuming that things intersect transversely, you just assume that the space where they intersect is 0, and then that's good. But it could have possibly made a bit more general, I guess, for the reasons you explained for the local model.
Well, so I believe it can be made more general, but it's not so clear what does intersect transversally mean here.
Okay, maybe we can think about it later.
Yeah, I mean, the short answer is I don't know.
Side remark.
But it's
proving this is already hard enough, so yeah, please go on.
It's a good question, for sure. Yeah. Okay, so let's look at the one example that I promised. So we need two ingredients. We need the G2 instanton theta and the Fueta section. So first, let's look at where does the G2 instanton theta come from. So we are in this situation of the manifold from before. X is our K3 surface. Beta is an anti-holomorphic involution, which comes from complex conjugation on CP2. And now fix some complex vector bundle E over X. Then we have the Donaldson-Uhlenbeck-Yau theorem, which tells us that Hermitian-Yang-Mills connections A on E are in one-to-one correspondence with stable holomorphic structures on E. And in the presence of an anti-holomorphic involution, you can upgrade this correspondence as done by Shuguang Wang, and you can say that Hermitian-Yang-Mills connections invariant under beta are in one-to-one correspondence to stable holomorphic bundles such that beta star E is isomorphic to E star bar. And this you get from looking how beta acts on the space of Hermitian-Yang-Mills connections and acts on the space of holomorphic structures. And so if you have such a holomorphic structure, such that beta star is E isomorphic to E star, E bar star, then you call this a real holomorphic bundle. And conveniently, we have such an example. Take curly E to be the bundle pi star of T star CP2. That's then the only stable rank 2 bundle over X. And because it's the only bundle, well, we must in particular have that beta star, E bar star, is the same guy as E. So if your moduli space only has one point, then that point is a real point. And you can observe that the trace-free endomorphisms of E is a complexification of some SO3 bundle F, which, so just like E through this correspondence, E carried a Hermitian-Yang-Mills connection, and then F will also carry a beta invariant AST instanton. And as said before, if you are given an AST instanton on X and you pull it back to T3 times X, then you get a G2 instanton. And the things to check is that it's rigid, where the beta invariance is clear because because we used this theorem above, and the alpha invariance is also easy to see because because we pulled something back from CP2, alpha swaps the sheets of CP2, so alpha does nothing here. And the rigidity is something you have to check as a calculation. And the second ingredient, the Fueta section, comes from the following theorem. There's a theorem from Gocho Nakajima, and they say if your gauge group is UN, then for any monotomy at infinity, there exists an infinitesimally rigid AST instanton on Iguchi-Hansen space with this monotomy. And luckily for me, Thomas Walpusky showed that that's also the case for gauge group SO3. So what you can do now is you look at your G2 instanton theta. This has some holonomy around the fixed point set of alpha and beta, and whatever holonomy that may be, you just take S to be the constant Fueta section, which takes as its value this compatible ASD connection given by the previous theorem. So then you get a, you have that everything is rigid, the theta was rigid, Fueta section is rigid ASD instantons, so by the theorem you can glue them together. And that gives you one example of a G2 instanton. Now I have some minutes left, so I can tell you about another half example. And that's in the following situation.
So just to ask a question, Daniel, okay? So is this a new example then of the G2 instanton?
So I will come to this. Probably yes. So yeah, well,
Thanks.
Let's say probably less. Probably yes, and I will make this precise in a minute. So the second example is a bit more exciting because that involves a non-constant Fueta section. So if we're in the case of T7, flat T7, and I'm looking at the example from Dominic Joyce's original paper on compact G2 manifolds. There we have a group generated by 3 elements, alpha, beta, gamma, acting on T7. And so on the orbifold, so on the regular part of the orbifold T7 mod gamma, we can get a bundle as follows. We can write down the fundamental group of this regular part of the orbifold that has 3 generators which come from the G2 involutions, and then 7 generators which come from the circles in the T7. Then there exists a flat SU2 bundle with some prescribed monotony representation, and we can, for example, prescribe the following monotony representation. We want that alpha, beta, gamma are sent to -1, and everything else is sent to 1. Then one can check again through a calculation that this guy is infinitesimally rigid. So that's our first ingredient, that's the G2 instanton. The second ingredient is the Fueda section. So on T7 mod gamma, we have that the fixed point set of gamma is 16 disjoint copies of T3. So flat 3 torus. So let's focus on one of these 3 tori for a moment and take coordinates x1, 2, 3 on this 3 torus. Then we can use the following theorem from Kronheim and Nakajima, who say that there exists a connected component C of the moduli space of ASD instantons, which is itself isomorphic to Iguchi-Hansen space. So what I'm really doing now is I write down a map from T3 into Iguchi-Hansen space and want that this satisfies the Fueda equation. And the way to get this map is the following. Just focus on 2 coordinates. So take the 2 torus given by x2, x3. This is an elliptic curve, so it has a Weierstrass map into CP1. At the same time, there exists a holomorphic curve in Iguchi-Hansen space, namely the bold of Iguchi-Hansen space. So there exists a holomorphic embedding of CP1 into Iguchi-Hansen. Then from this P we can cook up our Fueda section as follows. So map S from T3 to Iguchi-Hansen. You write this thing down, which is written down there. And then from the holomorphicity of P, it follows that you have this ds of del x2 minus I ds del x3 equals 0. And now if to this equation you apply J, then you see, well, you get J of ds of del x2, and J times I is minus K by these quaternion relations. So this is exactly the Fueda equation of a map that's independent of one coordinate. So that's also nice because these solutions to the Fueda equation, they're expected to be many of them, but not many of them have been written down, so it's not so easy to write them down. But the annoying thing is this is not rigid. So exactly here we would like to have some way to deal with non-rigid ingredients. Potentially, one trick to get around this, so to apply this very easy gluing theorem that I have right now, potentially one way to do this is the following. Perturb the G2 structure of the orbifold and hope to get a rigid Fueda section. So why would you think that anything like this is true? Is the following. It's that in favorable situations, so if you have a Fueda section into a flat manifold, then you actually know that solutions to the Fueda equation are extremal points of a function on the space of all maps. And then if you wiggle this function a little bit, then well, right now we have a whole T2 of extremal points, and after wiggling you would expect that you have some isolated extremal points. Now, if your target manifold is not flat, then you don't have this interpretation readily, so I don't really understand I don't really understand this. I'm not sure if you can do this to get a rigid Fourier section in this case. But one might hope that yes, it's possible. Okay, so that was the half example. Then one last thing I want to do. So what's up next? Well, I don't want to bother you with a lot of details, but just to say this, I will go through it quickly. First, it's not so hard to find more real stable holomorphic bundles on CP2 using the monad construction. So if you take bundles A, B, C and maps between them, little a, little b, then you can write down this monad, curly E, defined to be kernel of beta, mod image of, kernel of B, mod image of A. And, well, if you choose your A and B correctly, then you will find that this thing is a vector bundle. Now, reality amounts to checking some diagram commutes, the diagram on the right here. So that's something that's not so hard to check. And stability of your monad turns into an algebraic condition if your monad is of the form A, B, A, which is also not so hard to check then. The nice thing is, for rank 2 bundles on CP2, actually every stable bundle comes from this monad construction. So one thing you could do is you could describe the moduli of all real stable bundles on CP2 using this monad construction. That's probably not super hard. Now the next one is super hard. That's what I lamented to earlier. That it would be nice to glue non-rigid ingredients, and I don't really know where to start. I don't really know how to do that. And another fun question where it's not obvious whether it's easy or hard is the following. The manifold that I explained earlier from the Joyce-Karigiannis paper, T3 times x mod, or the resolution of T3 times x mod alpha beta, it's suspected that you can also get this from the twisted connected sum construction after stretching your 3 torus a little bit. Now, on the twisted connected sum construction, we also have some instantons. And it would be interesting, well, first to verify, are these G2 manifolds actually the same? And then to check, are these instantons? So can this instanton that I have written down also be constructed through the twisted connected sum construction? So it would actually be quite exciting if this was not a new example, I think. But for example, if you don't stretch your T3, then this example of an instanton is definitely one you would not be able to construct through other means. Okay, so yeah, there are some to-dos for the future. And I think that's all I have to say for today. Yes, that's the last slide. So thank you very much for listening, and that's it.
Okay, Daniel, thank you. I'll ask the first question myself, and then I apologize. I'm gonna have to leave. Have admin duty in 5 minutes. So just to expand on my previous comment about the non-rigid situation, right? So typically when you're gluing instantons, you want them to, the instantons on each side, you want them to match in the moduli space over the gluing region, right? And then, and the point is that because the manifold at the base has been constructed by a perturbative argument, you perturb using the implicit function theorem, you want this matching, this glued instanton to survive as an instanton when you perturb. Now, which means that there shouldn't be, when you perturb the base, this shouldn't lead to a bad deformation of the glued instanton. Now, one way to make sure there are no bad deformations is to make sure there are no deformations at all. Right? So rigidity is very reasonable, and it's the first thing you should ask. So if there's no deformations at all, then we should be good. But the next best thing would be if the deformation classes of the instantons from both sides intersect transversely at the moduli space, but because then they would still be resilient to a little perturbation, right? So that's, but of course, then the coordination model gets much harder, and it's, I mean, by all means, this is a great job. I mean, it's hard enough to work with the rigidity assumption. Probably next thing I may want to look at is perhaps the in the twisted connected sum case. This is exactly how the problem appears, right? To first assume rigidity, because then there are no deformations. Deformation space, you know, the intersection of deformation. There are no deformations, so there can't be any bad deformations. But in the general case, you could potentially have good deformations, which are not the end of the world. So maybe the twisted connected sum case contains some of the sort of basic insights which Thomas Volpuski has taught me in back in the day. So maybe some of his insights are still there.
Yes. Okay. Yeah. Now I understand the question. That's fair enough. That's a good next thing to look at, but I haven't looked at it yet. Yes. But now I understand.
Okay. Good luck. And goodbye. Thank you very much.
Yeah. Thank you. Any other questions?
Yeah, I'll take over as chairman. But is anyone has a question for Daniel? No other question or comment? Well, okay, then let's thank Daniel again.